Hey guys, welcome to Safi Mixed. In this video, I will let you know about the concepts related to graphical representation of vectors. In several cases, it is easier to solve problems of practical importance through geometry. For this purpose, when the geometry involves vector, we use graphical representation of vectors. So, in order to represent vectors graphically, we need to make some arrangement to fix the magnitude and the direction of vectors. So, we will understand how do we fix the direction of a vector and how do we fix the magnitude of vectors through graphical representation. But let me begin with the definition of graphical representation. If we have a vector, whatever it may be, irrespective of its dimension, irrespective of its unit, we represent symbolically, let's say, this vector with A. So A is a vector, then graphically this vector is represented with a line and an arrowhead at one end of the line. Then the length of the line represents magnitude. And the arrowhead represents direction. So a vector is graphically represented with a line and with an arrowhead. The line represents magnitude, the arrowhead represents a direction. Now this line is called the representative line of vector A. Now that's enough. So that's the graphical representation of vector, but there is a little more story. How do we fix the direction of a vector? Because if I drawn this vector in this direction, the magnitude of these two lines is still the same. But there is a problem. The arrowhead, one is pointing in one direction, the other is pointing in another direction. So we need to fix the direction of a vector. And that is done through geographical indicator. That is, we draw two perpendicular lines. This represents north, this represents west, this represents south, and this represents east. Now, how do we use this? In statements, we say that a vector is pointing in the direction of east. When that's the case, means we would draw a representative line in this direction. Similarly, when it is said a vector is pointing along north, we will draw a line parallel to north in the vertical direction. And when it is said that a vector is northeast, that means we are exactly at the mid of this point, so we'll draw a vector in this direction. And in other cases, if it is said that a vector is 20 degrees from east to north, that means we would draw a vector in this direction making a 20 degrees with east. Similarly, the statements could be a vector is pointing from north to west with 40 degrees. So then I will draw a line like that with an arrowhead, and this angle then be equal to 40 degrees. So we use geographical indicator to represent the direction of a vector to fix the direction of a vector. But remember, this type of indicator, this type of direction indicator is used usually in navigations, in airplanes, and somewhat in traffics. But in physics, we switch from this type of indicator to another one, which we call Cartesian coordinate. And I'll talk about that in the next video, our second next video. But for the time being, we fix the direction of vector by this geographical indicator. And the next thing, so according to this indicator, now this vector represents one direction and this vector represents another direction. Therefore, they both do not represent the same vector. This is one kind of vector, this is another kind of vector. That means the direction changes one vector to another vector. So two vectors, so two representative lines represents two different vectors. So this is one representative line, this is another representative line, so this is one vector, this is another vector. Now the next thing is, how do we fix the length? Is that arbitrary? No, the length is not arbitrary. To fix the length of a vector, we take the help of scale. And we construct with this indicator, geographical indicator, the next thing is to fix a scale. And now scale does two things. Number first, scale adjusts length. Number two, scales converts units to the unit of length. So how do we construct scale? That is, there are two things that we do with the help of scale. Number first, adjust lengths. For example, if I only talk about the displacement vector, then there could be different types of displacement, very large and very small. For example, one displacement could be 50 kilometers, the other could be 10 kilometers, or there could be a displacement of several hundred kilometers. So how will we adjust 10 kilometers, 50 kilometers, and hundreds of kilometers on a paper, on a board? So that's in fact, the job of scale. We choose our scale such that to accommodate our vectors within the available area. So we define scale like this: 10 kilometers equals 10 kilometers equal 2 centimeter. Then let's say I'm dealing with another displacement of 50 kilometers, then this will equal to 50 divided by 2, 50 divided by 10 into 2 centimeter. There will be kilometer, there will be kilometer, so that kilometer cancels with this kilometer. So with this, I would be left with 10 centimeters. Similarly, I can take another displacement, let's say of 20 kilometers, then this would be equal to 20 divided by 10, kilometer over here into 2 centimeter, and this would give me this cancel with this with this 4 centimeters. Now additionally, we would be given the direction. For example, this displacement is 20 degrees from east to north, so then I would draw a horizontal line like this and we draw the displacement in this direction of 10 centimeters. So I'll draw a line of 10 centimeter in this angle, then should be 20 degrees. So that's then the vector or graphical representation of this vector. Similarly, for this one, what I do, let's say this is 20 kilometer displacement from north to east, this one 40 degrees from north to west. Then in order to draw the representative line of this vector, what I'll do, I draw dotted lines. This one is not, so I'll draw a line of 4 centimeters, making an angle 40 degrees with the vertical line, with the north line. So then this is the representative line of this vector, this is the representative line of this vector. Now let's, instead of displacement, we have another physical quantity such as force. Then obviously the unit of force is not kilometer, it is Newton. In that case, what we do, we define our scale such as like this: 10 newtons equal 20 centimeter. So by this assignment, I convert the unit of force into the unit of distance, and then I scale the magnitude 10 to 2. So 10 newtons is equal to 2 centimeter. Then obviously, if I use the same thing, 50 newtons equals 10 centimeter, and 20 newtons would be equal to 4 centimeters. If instead of displacement, these vectors were forces, then this would be force 10 centimeter acting from east to north at 20 degrees, and this would be the force of 4 centimeter equivalent to 20 newton acting from north to west at 40 angles. And if we need to convert back our forces, our lengths, our vectors to the actual units, then we use again the same graph. For example, for 22 centimeter equals 10 Newton, then 4 centimeter would be equal to 4 divided by 2 centimeter over here, multiplied with 10 Newton. So this cancel with this cancel with this gives me 2, and I get 2 tens are 20 Newtons. So I'm back at 20 Newtons. So this way, at the end, we reconvert after graphical representation. If you want the actual answer in the actual units, what we do, we reconvert as per the chosen scale, the lengths of the vectors into the given units. So this is how we use graphical representation. If I review it simply, we first consider the representative line, and the representative line is drawn according to the geographical representation and the given scale. And the scale does two things. It converts the unit of the given physical quantity into the unit of length, and scales the length of the vector, the magnitude of the vector, as we wish. We can increase and decrease this choice. We can increase and decrease 10. For example, we can fix our scale such that 1.5 Newton be equal to 3 centimeters. That's our will. That's we are totally free in defining our scale, in defining the length of our scale. So this is what we call graphical representation of vectors. Oh, I'm back because I forgot one very important thing regarding the graphical representation. If I draw vector A like this is vector A, and this is the representative line of vector B drawn according to the scale that we just discussed. Then the two ends of the vector, the two ends of the representative line has special names. The end with arrowhead is called head of the vector, and the opposite of the head is called tail of the vector. So we have head of the vector with arrowhead and tail of the vector to the end with no arrowhead. You may see that sometimes vectors are also represented on signboards, etc., by putting a cross type thing at the tail. So this is equivalent to this, but this is used in signboards, etc. For graphical analysis of vectors, we don't use this thing. So that's an additional thing that I forgot, and I came back to tell you this. Thanks for watching.